Hello. In this video, we are trying a few more numericals on the electric field and electric forces of the electrostatics portion in the Standard 12 physics for the higher secondary schools. And one of the popular books that I'm following right now, and I'll be trying some of the exercise questions that have been provided in that. To begin with, I won't be doing all of them because there are at least I have selected 51 of them in this video. So out of those 51, I'll be doing the important ones which usually students find difficult to approach. Like for the case of the sixth question in this page, that we can see that two charges of 2 microcoulomb and 1 microcoulomb, it's given in 10 to the power minus 6 coulombs, so that's micro, and they are placed at a separation of 10 centimeters. So they are separated at a distance of 10 centimeters. Where's that gone? And in that separation you have to place a charge. So there's that 10 centimeters mark, and in that 10 centimeters you have to place a third charge. So a third charge needs to be placed so that the so that it experiences no force due to the given charges. So that's the question. We'll see how we can approach that. And so that's the sixth one that I'm trying right now. So there are two charges, 2 microcoulomb and 1 microcoulomb, and they are separated by a distance of 10 centimeters. Now, where should I place a third charge so that it experiences no force? Well, the third charge won't experience a force at a point where the electric field, the net electric field is zero. And obviously, because these are two positive charges, I have already provided the idea in the previous video. If you can go through that, you will find the conditions where which tells us about where the where the third charge must be placed so that it experiences no net force or no net electric field. And in this case it will be lying somewhere in between these two charges. Let us say that it is lying close. It will obviously lie closer to the 1 microcoulomb because that will be applying a force less than the 2 microcoulomb for equal distance of separation. Now, if we place it near 1 microcoulomb, the force of repulsion will be therefore equal to the force of repulsion that it will be experiencing from the 2 microcoulomb, which is at a distance of 10 minus x, considering the total distance to be 10. So from that what we get is the forces obviously have to be balancing one another, as a result of which this third charge, let us say that charge is q. It is immaterial actually what amount of charge is placed because it is going to experience a zero force nevertheless. So the condition being that the two forces are equal and opposite, obviously we'll have to consider a positive charge in between which will be repelled, or even a negative charge which will be equally attracted on either side. So the condition here is K 2 microcoulomb times of Q divided by 10 minus x squared, and that's for the first one, and that has to be equal to the force that is applied by the 1 microcoulomb charge. So K times of 1 micro times of Q. Obviously the Q is going to cancel out. A lot of other things are going to cancel out as well. Not only the charges Q and Q, the micro are going to cancel out, the K terms are going to cancel out. So all that remains is 2 over 1 if I take it on the right hand side, and then 10 minus x over x entirely squared. And so if we take the square root of that, or the either side square root, then we have 2 square root of 2 and then 10 minus x over x. We can cross multiply that, so root 2 times of x and 10 minus x, and that x can go to the other side, so we have root 2 plus 1 times of x to be equal to 10. And remember 10 was in centimeters, so obviously we will be getting the value of x in centimeters. Now this is 10 over root 2 is having the value 1.414, and that divided by uh, and that added to 1 is going to give us 2.414. Approximately, had it been 2.5, we would have got the result to be exactly 4, but this will be something near about, I guess, 4.1 or 4.2 centimeters, considering the value in the denominator being 2.4. So that's more or less the answer in this case, to 4.2 centimeters. From where? From the 1 microcoulomb charge, because that's the distance x that we have chosen. Now if we are to consider the distance from the 2 microcoulomb charge, it will be 10 minus 4.2, which is 5.8 centimeters. You choose wherever you wish to find that, with respect to whichever charge you wish to find. Now in the seventh one, if you see that there is the case that the second charge in the previous problem, if that is replaced by a negative one, that is minus 1 microcoulomb, then we will the location where the charge, where a positive charge placed, uh, or even a negative charge placed, will experience no net force. So for that, again, we have to look at those conditions. I'll just provide you with the answer directly. For the conditions to consider, you will have to check the previous video on this playlist of problems related to electrostatics. So now, as far as the seventh one is concerned, we have the same condition, but only thing is that we have minus 1 microcoulomb over here and 2 microcoulomb over here. Obviously, minus 1 microcoulomb will be attracting a positive charge. We'll consider a positive charge uh, for ease sake, and it will be attracted by the minus 1 microcoulomb, while the positive charge has to be repelled. So if I place it close to this, because minus 1 is less than 2 in terms of magnitude, so obviously the distance will be, in comparison to the 2 microcoulomb, the distance where the impact of the minus 1 is felt will be fairly less than 2 microcoulomb. So it is ideal that I keep the charge which is to be balanced by both the forces from both the given charges, that will be placed near the minus 1 microcoulomb. So that will be attracted by the force due to the minus 1 microcoulomb, and that will be repelled by the force due to the plus 2 microcoulomb. And nevertheless, the distance should be such that both the cases, or both the forces, must be equal to one another. We take the distance again here to be supposedly x, that is the distance that we put over there. So now the conditions remaining the same. This is 10 centimeters, of course. So from the 2 microcoulomb charge, as you can see in the above case, we just cancelled out everything on this step, and we ended up like this. So the ratio is again going to be 2 over 1. So instead of 10 minus x, this will be 10 plus x this time, because the distance is greater than 10, and on the other side of the 1 microcoulomb, which is negative in this case. And this is 10 plus x over x whole squared. So the same condition, only the thing is the difference in distance as opposed to the previous case. So now this is root 2, and this is 10 plus x over x. So that gives me root 2x is equal to 10 plus x. And so now I have root 2 minus 1 of x. So x is now equal to 10 over root 2 minus 1. Root 2 is obviously 1.414, and minus 1 is 0.414. Nearly it would have been 5. Had that been 0.5, it would have been 20, but now it is less than 0.5, approximately 21 or 22. Maybe you can check for yourself. I'll stick to 21 centimeters as of now. You can check. It's actually a bit more than 21. I guess it will be nearly 24. You can calculate by yourself, somewhere near about that. I'm just giving you an approximation. You can use your calculators, or even calculate that manually. Now, as far as the eighth one is concerned, two charged particles are placed at a distance of 1 centimeters apart. What is the minimum possible magnitude of the electric force acting on each charge? Now, the minimum force that you can consider is the minimum is related to the minimum charge, because the distance over there is fixed, that is 1 centimeters. So that need not be changed. The only thing that we can consider for a minimum possible magnitude of electric force is that the charge must be minimum, and the minimum possible charge that we can consider is that of the electron or proton. Obviously it hasn't told us about the nature of the force, so it can be either attractive or repulsive. So you can consider one electron and one proton, or two protons or two electrons. So in each of those cases, the charge remains the minimum possible amount, that is 1.6 times of 10 raised to the power minus 19. Remember, that is the minimum amount of charge that you can consider, because anything less than that isn't really possible as far as quantization of as far as the principle of quantization is concerned. So that will be the way to approach it. So I won't be doing that. I've just instructed you. As far as the ninth one is concerned, let's see that we have to estimate the number of electrons in 100 grams of water, and how much is the total negative charge on these electrons. So 100 grams of water. Now, as you know that water, 1 mole or 1 molecule is 18 grams. That is 18 grams of water constitute 1 mole, which comprises of Avogadro's number, that is 6.023 times of 10 raised to the power 23 number of molecules. Now, for 18 grams of water containing that many number of molecules, 100 grams of water, so you can take the unitary method. So 18 grams, so 1 gram will carry 6.023 times of 10 raised to the power 23 over 18. This will be the number of molecules that will be present in 1 gram. So for 100 grams of water, the number of molecules that you can obtain is 6.023 times of 10 raised to the power 23 over 18 times of 100. So that is the amount of that is the number of molecules that you obtain for 100 grams of water. Now, in 100 grams of water, each water molecule will carry 10 electrons, because 2 from 2 hydrogen and 1 and 8 from an oxygen. So there will be 10 electrons in all. So the total number of electrons that was asked, we obviously wanted the total negative charge that is possible. So the total number of electrons in the first place is this much, that is, we can take that as n. We won't be calculating it right away. And as far as the case of total charge, total negative charge is concerned, that will be only because of these electrons that are present. And so we know from quantization Q is equal to Ne. So N being this value, 6.023 times of 10 raised to the power 23, and we can take that as 10 raised to the power 3, and this is 18. And then for E, we know the value, that is 1.6 times of 10 raised to the power minus 19. So that gives me the value near about, well, we can calculate that 1.6. Instead of 1.6, I can take it as well, I can take it as 16, and take this as 10 raised to the power minus 20. It's all the same, and 16 can cancel out with the even numbers 8. Now 6.023 can be approximated as 6, so that cancels out with 18 3 times. And as far as 16 over 3 is concerned, that's nearly about 5.33. And considering the powers of 10 over here, there's 10 to the power 26 over here, 10 to the power minus 20, so this is 10 raised to the power 6. So this is the amount of negative charge that we can consider for 100 grams of water. And of course, this being due to the charge that is given by the electrons. Remember, the number of protons are also the same as that of the electrons. So in this case, we'll be getting a negative over here, because that is the amount of negative charge that we are going to get because of all the electrons. Now all the protons will add up and give the same amount of positive charge that will make the entire thing neutral. I'll straight away jump to the 15th one right at the bottom left. That is the attractive nuclear force acts. If you have any doubts in between, you can just write that down in the comments, and I'll try and solve it in another video. But they are fairly easier ones, so I I thought of going right down there on the 15th one, which looks pretty interesting. Now, the attractive nuclear force that is given by that is between two protons is given by this. This is obviously the comes from the Yukawa potential and Yukawa energy. So that force that we have F is equal to C e raised to the power minus KR whole divided by R squared. We need to write the dimensional formula and appropriate SI units for, well, for what? Well, that's for C and K. And also what we need to consider is that suppose K is 1 Fermi inverse. Now Fermi, as you know, is the measure of length, and so from that actually you already know the dimension of K that was asked in the previous bit, so it's going to be length inverse. But nevertheless, K is equal to 1 Fermi inverse, and the repulsive electrostatic force between the protons is just balanced by the attractive nuclear force when they are at a separation of 5 Fermi. We need to find the value of C. So first of all, let's see how the dimension goes that has been asked in the first bit. So for the 15th one, we have the force, the nuclear force between two protons to be given as F is equal to C e raised to the power minus KR over R squared for the distance of separation being R between the two protons. Now what it has asked is that it has asked us to find the dimensions of C and K. Now, as you know that exponential term and the trigonometric terms, they do not have any dimension or unit associated with them. So this thing over here is a dimensionless quantity that will be just a number. And what we are left with is C over distance squared, because R is the distance and F is obviously the force. So the unit and the dimension of C is going to be, C here being the constant, so unit and dimension of C is going to be Newton meter squared the unit, and the dimension is going to be the dimension of force multiplied with the dimension of distance squared, so that is m L cube T minus 2. That is going to be the case of dimension associated with the constant given. As far as K is concerned, K has the unit, obviously, as you saw, it is Fermi inverse. Nevertheless, it has length inverse, so we'll keep it as meter inverse. And the dimension K is equal to L raised to the power minus 1. Now, this is from the data that has been provided that I'm saying, but as far as the concept is concerned, what you know is that the exponential is a dimensionless quantity, as I said, and the power terms must be dimensionless as well. So for these things to be dimensionless, with R having the dimension of length, because that represents the distance between two protons, K has to be length inverse so that the dimensions cancel out to give a dimensionless quantity at the top in that power term. So with R having the dimension of length, K must have the dimension of length inverse so that they multiply to cancel out and give no dimension quantity, that is L raised to the power 0. So that's a dimensionless quantity, of course. So from that also we can determine the dimension of K. And as far as the unit is concerned, well, because the scale here is in Fermi, the unit will be Fermi inverse. But nevertheless, for in general, with the L inverse taken into consideration, we can take meter inverse as the unit as well. Now, as far as the force is concerned, which just balances the electrostatic force of repulsion between the protons when they are at a separation of 5 Fermi, let's check that. So R is given to be 5 Fermi. So in this case, what we find is the second bit B, that the electrostatic force of repulsion that is given by K, the charge of the proton, suppose, is E squared over R squared. That's the electrostatic force of repulsion, and that is balanced by the force that has been provided, that is C e raised to the power minus K. Remember, here the K is different I'll rather take it as 9 times of 10 raised to the power 9, just not to confuse you. So there the electrostatic force constant is K. Here K is obviously the constant that is associated with the uh, attractive nuclear force, and this R is given to be 5 Fermi, and here it is R square. Now K has also been provided over here, that is C e raised to power, this was 1 Fermi, and this is 5 Fermi inverse. So 1 Fermi and Fermi inverse, they are obviously going to cancel out. The R squares are going to cancel out. So all that remains is e raised to the power minus 5, C e raised to the power minus 5. Now this e is obviously again the exponential term. And this e is the charge. Just to tell you what we are doing. So this charge is obviously 1.6, so 9 times of 10 raised to the power 9 times of 1.6 times of 10 raised to the power minus 19 squared, and we wish to find C, and the term that is going to get divided over here, cross multiplied, that is e raised to the power minus 5. Now C therefore will be equal to, well, you can multiply that, that's nearly 23.04, which you must be knowing by now, having calculated all those numbers pretty frequently, and 10 raised to the power minus 29 for those numbers at the top, and E, if you know, is 2.71, and when that goes off, the power term becomes positive. So you multiply all of that and you find the value of C, and you put in the dimension of C, put in the units of C, that is Newton times of meter squared. So that is going to be your answer. You can check by multiplying and putting those values over there, and check for yourself what will be the answer. And up next I'll be trying the 17th one. The 16th one has the same line of approach, but only thing is that that's an equilateral triangle in the 16th one, where the angles between the forces involved will be 60 degrees for that equilateral triangle. In this case we'll see how we'll proceed for the 17th one, which has four equal charges of 2 microcoulomb. Each are fixed at four corners of a square of side 5 centimeters. We wish to obtain the Coulomb force that is experienced by one of those charges due to the rest of the three. So let's draw the figure first to help us understand the concept that we are going to consider. So 17th one has four charges. Two microcoulomb each, and they are fixed at four corners of a square of side which was 5 centimeters in distance. So we need to obtain the force on one of those charges. Well, I'll name them first so that things get easier for us. So this is the point A, B, then C over here, then D. So in that cyclic order. Now let's say we wish to calculate the net force on the charge C due to the charges at A, B and D. Now B, all of them are positive, of course, so they will be repelling the charge at C. From the principle of superposition, all of them will be applying the forces individually, irrespective and independently, of course, because they won't be irrespective of the force that they will be applying on between themselves. So B will be applying the force on C along this line. So this is F that the charge experiences due to the force due to B, and D will be applying an equivalent magnitude of force but in that direction away from it. all the forces will be away from all of them. And so this is FD, and A will be applying along that line AC, which is the line of the diagonal. And obviously the distance over here is different, so the force FA will be different in magnitude as compared to FB and FD. So as far as the principle of superposition is concerned, the net force that will be acting on the point on the charge at the point C will be equal to the vector sum of the forces FB, FD and FA. So in terms of vectors, when we are going to add, we'll be adding two of them following the formula that we have obtained from triangle law or probably the parallelogram law, and then the resultant is going to get added to FA. As far as this FB plus FD is concerned, how we can say is that they have the same magnitude is because the two charges, the pair of charges that we are considering at B and C, as well as for D and C, the pair of charges have the same magnitude, that is 2 microcoulomb. And the distance of separation between BC and DC, that's also same. So what we know is that FB has the same magnitude as FD, and let us say that is F. We take this as F net. So let's say that this is F simply. And the angle between them is obviously 90 degrees every time. Take it on that side or this side. It's ideally on this side, that is between C at that corner between the two arrowheads. So the angle being 90 degrees, what we know is that the net force for them, let it be F prime, will have a magnitude of FB squared plus FD squared, that is 2F squared if we use this term over here. So that is root 2 times of F. Now what should be the force between A and C? The force between A and C, that is given by FA, that will have a magnitude equal to K. Well, as far as this F is concerned, it will have a magnitude, if you know, is K Q squared, because the two charges are the same, and we'll take 5 centimeters as R squared. This is the R that we are getting over here. Now if you know the case of diagonal, it is root 2 times of R for a given square. So that means here we'll be getting the force to be equal to K Q squared, because the magnitude are the same, and root 2 R squared is nothing but 2 R squared. So this is K Q squared over 2 R squared. And if you look at it, this is this value kq over r square, that is equal to f. So this is simply equal to f over 2, and it's going to act along this line. And what else is going to act along that line? That is f prime, that is the resultant of fd and fb. Why? Because when two forces are equal in magnitude, if you remember, I made a video on that. If two forces are equal in magnitude, the net force, the resultant force of both of them, it bisects the angle between them and is obviously going to act along that bisected line along which FA is acting. So therefore the net force now will be, at least for magnitude's sake, it will be root 2f, that is the resultant of FB and FD, and also FA, which is acting along the same line. So now this is going to be equal to f times of root 2 plus 1 over 2, or that is f times of 2 root 2 plus 1 over 2. And we know the value of f, we can just substitute those numbers that we have with us. So for f we have k, that is 9 times of 10 raised to the power 9, q squared, that is 2 micro, that is 4 times of micro squared is 10 raised to the power minus 12, over the distance, that is 5 centimeters taken in meters, will be equal to 5 times of 5 times of 10 raised to the power minus 4. That is the value over here. So 2 root 2 is 2.828, because 1.414 times of 2, 2.828 plus 1, 3.828 over 2. And if you put those values, you will find something. Let me see if I can help you with it. Now 9 times of 10 raised to the power 9, that stays as such. We'll get rid of those powers of 10, keep it separately. So there's a 9, there's a 4 over there. It won't be bad if I multiply a 2 over here. Why am I doing it? Because if I multiply a 2 over there, I certainly multiply a 2 in the denominator term. So that becomes a 2 over here, a 5 over here is 10. Another 2 that is multiplied, that is because of this multiplication, we get another 2 in the denominator, and this 5 also becomes 10. So 2 tens over there, so that is 10 to the power 2, and 10 raised to the power minus 4, this is 10 raised to the power minus 2 now. And the rest of the terms in the denominator have gone. And there's a 10 raised to the power minus 12 that stays at the top, and then we have the value 3.828 as well. So this is going to be 9 times of 8 is 72, 72 times of 38. Now 72 times of 38 will come to be nearly equal to, when it's 72 times of actually 3.8, so when it's 3.8, it's actually 4 minus 0.2. So 72 times of 4 is going to be 288. 288 minus 2 times of 72 is 144, divided by 10 is 14.4. So that's equal to 275.6. If I have written that, no, that's 273.6. 273.6. And if that is 273.6 approximately, so, and the powers of 10, as you can see, will be minus 10. So what I can write over here is 2.73 approximately, or I can take it as 2.74 rounding off, and then 10 raised to the power, because I have used 2 places, so it's 10 raised to the power minus 8 in newtons. You can check for any errors over there, and if you get any, you let me know, or you can just help yourself with the value that you obtain. Now in the 18th one, we have the case of the hydrogen atom, where the electron revolves in circles at a radius of 0.53 angstrom, angstrom being 10 raised to the power minus 10 meters, about the nucleus, which carries a single proton. And the hydrogen atom is said to be in the ground state in this case. So the magnitude of the electric force between the proton and the electron in the ground state has been asked. So that's fairly easy. But what's the case with the next question? That is what I want to try. The 19th one has the same case of the ground state of hydrogen atom, where the electrostatic force of attraction is provided. But that attraction obviously contributes to the centripetal force, that is for the electron when it is revolving about the nucleus carrying one proton. So that is what it has asked, that is the speed of the electron in the ground state is to be determined considering the case in the previous problem, that is the 18th one. So let's try the 19th one, taking the case of the 18th one. So we have the electron to be revolving around the nucleus with a radius of 0.53 angstrom units, and the electron obviously has a charge, negative charge, and the proton has a positive charge, and that force of attraction, the electrostatic force of attraction between the proton and the electron, is given by K E squared over R squared. R here is 0.53 angstrom, which is 10 raised to the power minus 10 squared. and that contributes to the centripetal force, as I said, which carries the mass of the electron me times of v square over the distance r, so 0.53 times of 10 raised to the power minus 10. mv square over r is the formula for the centripetal force. If you remember, we have a playlist related to centripetal force as well. You can go for that. Now this one of those values get cancelled, and the mass of the electron is approximately 9.1 times of 10 raised to the power minus 31. We can take it as 9 only instead of 9.1. Mass of electron 9.1 times of 10 raised to the power minus 31 kgs. We can nearly take, for calculation's sake, we take it as 9, and so v squared will be k, which is 9 times of 10 raised to the power 9, e squared 1.6 squared 10 raised to the power minus 38, that is minus 19 squared, and this is 0.53 now, 10 raised to the power minus 10, and the mass of the electron, which we have taken nearly to be 9 times of 10 raised to the power minus 31, so the 9's get cancelled out. V will therefore be equal to, well, let's check for the powers of 10 first. This is minus 31. As it goes up, it becomes plus 31, so plus 31 plus 9 is 40. 40 minus 38 is 2, and 10 raised to the power minus 10 going up makes 10 raised to the power plus 10, so 2 plus 10 is 12. Root over of that, because we are going to take the square root to obtain v, root over of 10 raised to the power 12 is 10 raised to the power 6. Now what terms are left? 1.6 squared taken under root is 1.6 directly, and 0.53, well, 0.53 is actually between it's actually, if you remember the square of 23, not 29, 23, it's nearly 529. 529, it's near about that value, but it's just 0.53. Had it been 0.53, then we would have had a perfect square in that. So that 0.23 that I'm talking about, that's not going to work over here, because 0.23 squared is 0.0529, but there isn't a zero, and if we consider a zero by considering the powers of 10, then that, well, we can do that actually. This can be taken as 0.0530, and that will be under root. And if I have taken a 0 over there, that means I have taken a 10 from that. I've divided it by a value 10, so I'll be multiplying a 10 over there, and I can take a root over of 10 there. So now this becomes 1.6, this is 0.23 approximately, and as we know, root over of 10 is approximately 3.2, 3.16 actually. We can take it as 3.2, and this one goes 2 times 3.2, so 1 over 4.6 times of 10 raised to the power 6, and 0.46, not 4.6, 0.46, 0.46 nearly equal to 5, approximately 2. We can take the value to be approximately 2.3, I guess, 2.3 or 2.2 to be precise. 2.2 times of 10 raised to the power 6 meters per second, so that's quite a speed considering the case of the electron revolving around the nucleus is concerned, almost relativistic case, and that is why for hydrogen we consider the case of relativistic motion. Now for that 20th bit, what we have is that we have 10 positively charged particles which are kept fixed on the x-axis at distances 10, 20, 30, right up to 100 centimeters, that is up to 1 meter. And the first particle carries a charge of 1 times of 10 raised to the power minus 8 in coulomb, and then For the second one, it's 8 times of 10 raised to the power minus 8. Third one, 27. And it goes so on. Like if you see that they are the cube of the distance factor. That is, for 1 it is 1 cube, 2 that is 20 centimeters it is 2 cube, and for 30 centimeters 3 cube, and likewise up to 10 times of 10 centimeters, that is 100 centimeters, it is 1000, that is 10 cube. And we wish to calculate the net force on the magnitude of the force that is acting on a 1 coulomb charge which is placed at the origin. So let's see how we can proceed with this. I would say, even if it looks scary, but it's fairly easy when you consider the case of series addition. So this is the 20th one. We have the charge at the origin. What we do is we calculate the net field at the origin and then we multiply that charge. So Q times of the net field is going to give us the net force. So this is 1, that is 10 centimeters, 1 times of 10 raised to the power minus 8 coulomb. Then that is 20, and it continues. So this is 8 times of 10 raised to the power minus 8 coulomb, and we'll take it to 100 centimeters over here, and that is 1000 times of 10 raised to the power minus 8 coulomb. So what we do is we calculate the net force. In order to calculate the net force, we first calculate the net field over there. The net field at the origin is going to have a magnitude, obviously, because all of those vectors are going to add directly, because the line of the force is going to be the same, and that is why they all will be acting, all the fields will be acting along the same direction. So obviously the net field is going to be the addition of all such fields directly, even in vector case. So kq over r squared for the first one, that being 10 centimeters. Now k is the common term for all of them, and also we keep the 10 raised to the power minus 8, that is common for all of them. And as far as the consideration of centimeters is concerned, that is also the multiples of 10 squared is 100, and for centimeters it's going to be meters, so square of that is 10 raised to the power minus 4. So all of that taken in common, and what we are going to find is that 1 cube over, because we have taken the 10 factor to be common in each case, this is 1 cube over 1 square when it comes to the distance, so we are left with 1. Then 2 cube over the square of 2, because the 10 has been taken common over here, which is squared to give 100. So 2 cube over 2 squared is just 2. Likewise 10 cube over here, and the 10 that is there, that is squared for the distance, and that is going to give us just the 10. So eventually what we are going to get is the sum of 1 right up to 10, and that comes up to as 55, because that is from the formula of series addition, n times of n plus 1 over 2, summation of n is equal to n times of n plus 1 over 2. So that means we are going to have this as, we put the values over there. This is 10 raised to the power minus 2 in the denominator, 10 raised to the power plus 1, because we have a 10 raised to the power 9 in k, so 9, and 10 raised to the power 1 is 90, and 10 raised to the power minus 2, so this is 9 times of 10 raised to the power 3, and this is 55, which comes from the totaling of these numbers. This is 10 times of 10 plus 1 is 11 over 2, so 10 times of 11 is 110. 110 over 2 is going to give us 55. So 55 times of 9 is 495, if you know. 495 can be written as 4.95 times of 10 raised to the power 5 Newton per coulomb. Now if I place a charge of 1 coulomb over there, so it's going to experience a net force of, in magnitude of course, is 1 coulomb into the net field. 1 coulomb just cancels out that coulomb in this case, so we have 4.95 times of 10 raised to the power 5 in Newton. as the net force that is acting on that 1 coulomb charge which is placed at the origin over here, uh, for the net field of that charge distribution along that line in the x-axis. As far as direction is concerned, if we are taking them to be the positive x-axis on the right hand side, the direction is obviously going to be on the left hand side, that is on minus I cap. So you can consider that as well. So I'm going to stop here and try that many questions as of now for this video. I'll be providing another video in this in those set of problems that I have. We have done up to 20. We'll be moving over and going to the next bits that are available to us, but that will be in the upcoming videos. Till then, stay tuned and thank you for watching.